In this video, the learner will calculate the geometric mean of two numbers and solve problems using right triangles and their altitudes. Think back to when you've talked about that word mean. It means average. There are actually different types of averages that you can take for a set of numbers. We're going to talk about the difference between two of those. First is one that you know is called the arithmetic mean. It's an additive average of a set of numbers. It just means that we would add the values together and then divide by how many terms there are. And that's the type of average that you're used to doing. So if I want to find the average of 6 and 24, I would add 6 and 24 together to get 30. And because there are two numbers, I would divide by 2. So 30 divided by 2 is 15. That means that 15 is the arithmetic mean of 6 and 24. The geometric mean of two numbers is a multiplicative average of a set of numbers, which means instead of adding the values together, we're going to be multiplying the values together and then be taking the nth root of that product. The nth root means how many terms there are, and that's the number of root we're going to take. So if I want to find the geometric mean of 8 and 18, I want to know what the multiplicative average of 8 and 18 are. So I'm going to multiply 8 and 18 together to get 144. And because there were two terms, I'm going to take the square root of 144 to get 12. That means that 12 is the geometric mean of 8 and 18. Another way to look at this is the arithmetic mean is an additive difference between the sequence of numbers. Notice in this sequence, the difference from 6 to 15 and from 15 to 24 is 9. And that's an additive relationship. If we add 9 to 6, we get 15. If we add 9 to 15, we get 24. However, in this geometric sequence, we don't have that additive relationship. If I add to 8 to get 12, that's 4. But if I add 4 to 12, I don't get 18. Instead, it's a relationship of ratios. Notice that I could multiply 1.5 times 8 to get to 12, and multiply 12 times 1.5 to get 18. So the ratio between each value is the same for geometric mean. Here, the ratio is 1.5. So the geometric mean is the number such that A to B is equivalent to B to C. So that number B is the geometric mean. In other words, we're trying to find the average ratio of a set of numbers. So if I am given 1 and 4, I want to find the number that I could multiply by 1 to get to this number, and it's the same as multiplying this number by that ratio to get to 4. Well, the geometric mean of 1 and 4 is 2, because I can multiply 1 times 2 to get to 2, but then I can then take this 2 and multiply it by 2 to get to 4. I could also use the ratios to help me look at this. So if I have 1 is to what number is the same ratio as that number to 4. So we would see 1 is to 2 as 2 is to 4. Those ratios are equivalent. We can check that by taking the cross product. 2 times 2 is 4, 1 times 4 is 4. Let's take a look at another set of numbers, 2 and 18. You might be able to guess and check this in your head. 2 times a number gets me to our geometric mean, and then our geometric mean times that same ratio gets me to 18. If you guess and check for a little while, you might find that the geometric mean is 6, because 2 times 3 is 6, and 6 times 3 is 18. We can also look at the ratios. 2 is to 6, as 6 is to 18. Again, check the cross products to make sure they're equivalent. 6 times 6 is 36, and 2 times 18 is 36. These two examples were very simple examples of geometric mean, but what happens when they're not so easy to think about? So how would we solve for the geometric mean? We're going to use ratios and proportions to do that. We want to find the geometric mean of 4 and 9. So let's let the geometric mean be x that we're solving for. We know by the definition of geometric mean that the ratio of 4 to x has to be equivalent to the ratio of x to 9. This is just a proportion that we can cross multiply and solve. So x times x becomes x squared, 4 times 9 is 36. X squared equals 36 is solved by square rooting both sides, and we get 6. That means the geometric mean of 4 and 9 is 6. Here are some practice problems on your own. I want you to find the geometric mean of each pair of numbers. Before we get into the next thing with right triangles, I want to review a little bit about similarity. When triangles are similar, remember their sides are proportional. So if I want to solve for the length of this side, that's b in this example, I would want to set up a proportion. There's more than one way to set it up, but you could set it up this way as 6 over b equals 10 over 18. And then solve that proportion. 10b equals 108, and then divide by 10. So the length of that missing side would be 10.8 units. Here's an example I want you to solve on your own. Solve for that length in this right triangle. Set up that proportion. Now here in this triangle ABC, we have drawn an altitude of that right triangle. This segment CD is an altitude of the right triangle ABC. So notice it's drawn from the right angle of the triangle, and the other point is on the hypotenuse of the larger triangle. What happens then is we actually form 3 separate triangles. We have the larger triangle ABC that has lengths A, B, and C. We have a smaller right triangle inside BCD, where BC is length A, which is the exact same as the length A in the big triangle. And then H and Y are the legs of that smaller right triangle. Then we have an even smaller right triangle, ACD, where X and H are the legs and B is the hypotenuse. But B is the same as B for the larger triangle. Notice that length AC is going to be the same segment AC for the larger triangle. Well, notice we can actually prove similarity in these triangles. Because we know they all share right angles, because this was an altitude, so it created right angles. And the triangle to start with was a right triangle. So we know they have those angles in common. Between these two, we have angles C and D that are congruent, and angle B that is shared, which means it is congruent to itself. So we have angle-angle similarity here. In this larger triangle, we have the right angles C and D that are congruent to one another, and then this angle A that is shared. Therefore, the larger triangle and the itty-bitty triangle are similar. We also have angle D and angle C that are shared in both the smaller triangles. So we have angle-angle similarity there. Therefore, we know all three of those right triangles that are formed are similar to one another, which means their sides can be set up in proportions. And if we're given some of those missing pieces, we can use those proportions to solve. So for the bigger triangle here, we could set up the A to B ratio, or B to A, and that would be the same as H to Y in the middle triangle, or X to H in the smaller triangle. We could also set up the ratio of hypotenuses to longer leg. So notice in the larger triangle, the hypotenuse C to the longer leg A would be the same ratio as A to Y and B to H. We could also set up the hypotenuse to the shorter leg. So C to B is the same as A to H, which is the same as B to X. Now notice in each one of those circled relationships, they involve a geometric mean. So in a later video, we're actually going to connect these two concepts of the geometric mean and these similar right triangles. First, let's practice with the three separate triangles. In this example, I want you to draw and label the three right triangles created when the altitude ML is drawn in the right triangle, and then solve for X, Y, and Z using proportion. So we have the three triangles, AJKL, LKM, and JML. Now we know these are all similar because it's an altitude drawn inside a right triangle. We looked at the last example where we proved those triangles were similar. Whenever that happens, those triangles are always going to be similar. So when the altitude of a right triangle is drawn from the right angle, it creates those three similar right triangles. Now what you need to do is label the pieces. Well, in the larger triangle, we have the two legs, JL, which is Y, LK, which is Z, and JK is actually these two pieces put together, so it will be 25. In the middle-sized triangle, we have segment LM, which is X, segment MK, which is 20, and segment LK, which is Z. Notice that LK is the same as LK here. They're both the value Z. In the smaller triangle here, we have length JM, length ML, and length JL. Notice that ML is the same as this ML. They're both valued X. JL is the same as this JL. They're both valued Y. It's because those are shared sides for those triangles. The hypotenuse of the smaller triangle is the shorter leg for the large right triangle. What I want you to do now is use proportions to solve for X, Y, and Z. You're going to use triangle similarity to set up those relationships. Use only two triangles at a time. So if we want to solve for Z, notice we can use this triangle here and relate the hypotenuse, 25, to the longer leg Z, and the hypotenuse Z to the longer leg in the larger and medium-sized triangles. So that's the proportion you would want to use there. I want you to do those proportions on your own. And then I also have two more examples. Draw out the three triangles and set up those proportions.